You press the power button, but there is no light and no sound. The device is completely unresponsive right when you need it. A non-responsive gadget is rarely a total loss. Usually, it is simply the result of a physical break in the flow of power. Opening the battery compartment reveals the first layer of the system, the electric cells. Understanding the physics of these basic cells allows you to identify exactly where that power flow is failing. An electric cell is a self-contained chemical reactor. Inside, stored chemicals react to generate a steady stream of electrons. The cell has two terminals. The protruding metal cap at the top is the positive terminal, and the flat metal disc at the bottom is the negative terminal. This orientation is called polarity. Electrical energy moves in one direction. It exits the positive terminal, travels through the device's circuitry, and returns to the negative terminal. It functions like a river, where current flows from the higher potential of the positive cap to the lower potential of the negative base. Inserting the cell backward places two negative terminals against each other. The current cannot push against that barrier, and the flow stops. If polarity is ignored, the circuit remains open. Without a continuous path, the device cannot function. A single AA cell provides 1.5 volts. That isn't enough pressure to power a high-intensity LED flashlight. To reach the required threshold, engineers use a series connection. In this layout, the positive terminal of one cell touches the negative terminal of the next. This creates a single continuous chain. Stacking the cells add their individual voltages together. Two cells provide 3 volts, creating a stronger push of energy through the circuit. Series connections are used whenever a device requires cumulative voltage to drive demanding components. It is a common assumption that placing batteries side by side will also increase that power, but in a parallel connection, all the positive terminals are wired together separately from the negatives. The voltage remains at 1.5 volts. If the voltage stays the same, there is a different mechanical reason for this layout. Think of 3 pipes feeding into one reservoir. The water isn't hitting with more force, but you have 3 times the volume of water available to use. This layout increases total capacity. It won't run brighter, but it will operate much longer before the chemicals are exhausted. Parallel connections provide the endurance required for long-term operation. These two wiring concepts determine exactly how a device manages its energy supply. This split screen compares different engineering priorities. A flashlight needs high voltage. A radio needs long-term stability. The flashlight uses its series stack to generate the specific voltage needed to bridge the gap in its LED. The radio uses a parallel layout to draw a small amount of power over several days of continuous use. Battery compartments are designed specifically to match the unique energy consumption of the device they power. Effective troubleshooting starts with polarity, ensuring the positive and negative terminals align with the circuit's contacts. Recognizing a series connection identifies that the device relies on combined voltage to work. Seeing a parallel layout indicates the device is designed for extended runtimes. In the case of this RC remote, the fix was mechanical. Flipping one battery restored the closed circuit. Every time you replace a cell, you are re-establishing the physical path that allows electrons to move.